Thank you for having me. My name is Nikolai Smolensky, so I lead deep learning science team at Autonomous Vehicles Organization at NVIDIA. And so this talk is titled Towards Modular Deep Learning Based Navigation for Autonomous Driving. Okay. A bit of delay in slide switching. So the agenda I will present in general. So this talk focuses on self-driving cars. So we work on self-driving cars, and I will talk a little bit about the autonomous vehicle stack in general, and how can we actually push more of deep learning into this stack and use it in a practical way, which brings safety and verification problems. And then I will make an argument. So I will provide an overview of our perception networks and also networks for planning and control and prediction. And I will make an argument that it's possible to build a modular and deep learning system that's a little bit addresses better safety and verification issues compared to end-to-end learning, but still uses a lot of deep learning. And credits for this work go to people listed here. And also I would like to thank our leadership, David Nister, Ruchi Bhargava, and Rotam Aviv for support in our work. There were several attempts to use deep learning in end-to-end fashion for robotic systems, specifically some works listed here for drones and for self-driving cars. At NVIDIA, we created this drone at the bottom row in the middle that can do end-to-end deep learning, and then DAVE2 system on the left at the top was created by NVIDIA to do also end-to-end deep learning from pixels to control. So it was shown that it's possible to do deep neural networks end-to-end from pixels to control, but there were some downsides to this approach. So this approach captures complexity of the world quite nicely, but it may be hard to verify, to do safety checks, and to use it for practical systems that does more than just say lane following. So because when you approach an intersection, there's like a lot of different hierarchical tasks that are happening. And so one typical approach today to autonomous vehicle stack is pictured on this slide at the top. So you have localization mapping, perception, prediction, planning, and control. It's literally kind of like a pipeline that's flowing from left to right. A lot of code is handcrafted, and it's with some heuristics to handle complex cases. Not everything can be deep learned. Probably the highest component that is using deep learning is perception. Prediction is kind of transitioning towards deep learning. Other components are mostly coded with classical methods or some heuristic code to cover complex cases and long tail. The challenge, though, with the custom-made code is that the world is very complex, and we have a very long tail in autonomous vehicles to handle all these little cases that it is hard to capture, even with a lot of people coding the stack, all the complexities in the world. So certain things are easier to learn from data, although there are also things that are easier to do with engineering by hand coding specific rules and cases to give prior knowledge to the system. So just do a little bit of side note, this is our R&D vehicles. We typically are equipped with cameras and top roof mounted LiDAR, or actually several LiDARs, and then we have radars along the bumper of the vehicle. So we can collect a lot of perception information, and depending on which level we target, L2 or L4, we can use different sensors. And to start talking about my argument about this modular deep learning pipeline, so my talk will be kind of going from left to right in that pipeline, and the argument will be that we can actually convert most of these blocks into fully deep learnable modules, although representations between these modules can be fixed to some human understandable format so that we can verify and provide safety checks. So the first system is focusing on perception, specifically our multi-view LIDARNET, which we presented here at IROS as a paper listed down below. It looks at the scene. So in fact, it's a two deep neural networks stack as a pipeline. There is one neural network looks at the perspective view, range scan and perspective view, and second one looks at the top-down view, and we can detect cars, bikes, pedestrians, about up to 200, 300 objects in the scene with high accuracy, and we also can detect this green drivable space by segmenting it. And this is the demonstration. So the first stage, we start by segmenting the LiDAR range scan from the top part into the segmented mask, and then we convert it into projected top-down projected scan, and then that tensor is then used for object detection, basically. So pedestrians are detected as cylinders and cars as boxes, and we also do extra tracking with classical methods to do instance tracking. And the drivable space, the road surface, is detected as this green segmented mask by the first stage. And we can, like I said, we can detect up to 200, 300 objects. It runs real time on the car. And this picture shows the architecture of the network. It's sort of like a pipeline. So you have a first stage focusing on the perspective view. So it takes the range scan, we push it through the network, and we do semantic segmentation of this range scan. We can detect up to 24 classes quite nicely with high accuracy. Then we reproject this into top-down view, combine it with depth information or height at each vertical column, push it through another network that does top-down detection of vehicles and pedestrians and whatever objects we want. The free space that I mentioned comes from the first stage. Basically, we detect the road surface. So we do this approach because we think that certain features are much easier to detect in the perspective view semantically than in the top-down view, even though cars are possible to do in the top-down view. But metric, the output of the network should be an affordance that is useful to planning and control, which is a top-down representation of what's going on in the metric format. Just one perspective stage alone in segmentation is not enough for planning and control. Combining them both provides rich information for planning and control. And our network is on par in terms of accuracy with state of the art, but we are much faster running at 7 milliseconds on embedded GPU because we can afford to be shallower because of this two views approach. And one can argue that, so this is good for LiDAR because LiDAR can do rich metric information, but cannot be done for camera as well. And so this is our work on panoptic segmentation. So this is panoptic segmentation DNN that we created running on the car. Again, we detect cars, pedestrians will be coming up, and then also drivable road surface. Down below, you can see instance segmentation as well with a very rudimentary instance tracker. In this case, it can be improved further, but we were focusing on detection and also in detecting instances. But you can see that in the highly complex urban environment with lots of occlusion, we think this method provides nice semantic understanding of the scene with high accuracy. You can see here we detect road hazards like these cones, which are actually is a big problem to capture all possible cases that can happen in terms of road hazards. Highway scenarios. And then we're gonna coming up to a more dense urban scene with a lot of pedestrians. Again, here we can detect and track up to 200, 300 objects. This network follows fairly known encoder-decoder, UNet or FPN bottleneck architecture, where we have two heads. That one is doing semantic segmentation and the other one doing instance decoding. And then we use post-processing to actually decode specific instances. So this network, you can think of it as the first stage of the previous network that I mentioned for LiDAR. But for the second stage, we can use one of the neural networks that can compute dense depth. In this particular case, we use structure from motion multi-view network that computes depth from two sequential frames and eager pose of the vehicle. We also before worked on stereo depth DNNs and mono single frame depth DNNs that can also be used. But in this particular case, we provide quite nice and low error. D1 error on Kitty is about 4% in this case, and a little bit lower. Yeah, so we kind of compare this with monocular depth DNN. Structure from motion net actually provides much higher accuracy around shadows and objects of odd shapes. So this is the output point cloud of the structure from motion network compared to red LiDAR points. So both networks, both of these networks can actually be combined in a similar multi-view perception DNN, where as an input you have a first stage processing perception data in a perspective view. Then we can reproject it to the top-down view, maybe combine it with mapping information and other signals like ultrasound, and then do top-down object detection. This network can learn to correct for errors that come from camera depth networks. And you can also do end-to-end training of these networks by doing either using a latent space from this perspective view to the top-down view, to the top-down network, or doing more differentiable reprojection. So I talked a bit about how to convert perception completely from pixels with a deep neural network from pixels to the affordances that are useful for planning and control. And now I will move towards right to talk about prediction and planning, how to use these affordances. So the previous networks provide effectively obstacles plus some mapping features and a top-down representation. So these can be used to as a next stage to predict how they will move in the future, and then I'll show how to also plan eager motion around this environment. So in this particular case, we also trained PredictionNet DNN that takes top-down rasterized view of several time steps for all obstacles and their path locations plus the map. We push it through the network and it produces PDFs of future poses, and we also can extract trajectories. And this is the demonstration of this network. So we train it from LiDAR stack output, so it's a highly accurate output. As you can see here, that stack is using our multi-view LiDARNet for obstacle detection. And then we combine it with high definition maps as a separate layer. So the network basically is using several time steps of past motion plus the mapping information. And then with this information, we predict into the future. And this is the network running on the car. At runtime, we actually use camera plus radar data. We don't use LiDAR, so we train on LiDAR, but for the L2 level, we can use camera plus radar data. And again, we predict PDFs of future poses, and we can extract, we also regress motion vectors that allow us to extract specific trajectories. And a few cases. So this is how it predicts motion around the intersection. So some cars will go forward, some cars will turn. These cars will be still stationary. So we can predict that cars will stay. This is a lane change prediction with bimodal PDF. So you can see that the PDF overposes splits, and we can actually nicely predict with probabilities if the car will go forward or straight or change lane. This is lane change under the bridge. So this overpass is not being treated as an intersection, but the network actually understands that there is some height to this structure, which can be encoded in the input tensor. And this is the merging scenario. And this, so the following is roughly the structure of the network. So we use RNN or LSTM. The input information rasterized objects plus map is and their past location are pushed through to deconvolutional encoders, which goes into the internal RNN state, which then can be rolled out into the future, and we decode into the pixel metric space. So each pixel is roughly 30 centimeters in this top-down representation. We predict PDF of future poses and the motion vector field of how the cars are moving from pose to pose, from which we can extract information for specific individual trajectories. We can also, currently we extract unimodal trajectories. We can extract bimodal and n-modal trajectories. We also thought of, can we use this prediction net as a model of the world to do model-based reinforcement learning, and started doing experiments on, can we actually try to simulate traffic with the prediction net. We did few experiments to set up initial poses of cars and then let prediction net roll into the future. Effectively, you can sample into the future. So the following video will show how this DNN can simulate traffic. So we set up initial position and then let prediction net do n steps of prediction, and then take first step, push it through the simulator, rasterize again, push it through the network, and then roll out the future that way. You can see the green is the EGA vehicle, so we also predict likely motion of the EGA vehicle. So you can see that the DNN is capable of predicting into the future. There are some errors, of course, like here, but for the most part, they do behave reasonably okay. So this is like around fairly complex intersection. It still knows that these cars will move this way, these cars will move that way. Some of them, again, there are some mistakes. It's not perfect, but we're moving towards using a DNN trained from real data to be used as a model of the world. So the powerful thing about this, you can then use model-based reinforcement learning, and effectively you can run your train your simulation from the real world. And we tried exactly that to take a very simple case of ACC, our active cruise control, and train a RL policy that is capable of, so basically it's trained from the output of prediction net, but it's doing some scenario that's a little bit more sophisticated for the planning and control. So in this particular case, we're gonna show the video of the green car is controlled by RL policy. It needs to follow this magenta car. The cyan car will try to cut in front of green car, and the green car needs to nicely follow magenta car and prevent the cut-in from happening by the cyan car. And on the left, we will show the learned Q function for this case. So in this particular case, so this Q function consists of steep curves. So each curve presents the position distance of the green vehicle to magenta vehicle at some time from 0 of decision making to 0.8. Each curve corresponds to sort of acceleration that's been chosen for a given time. a red means lower score that you don't want to use, and then green means a more desirable score that you want to use. So in this particular configuration, green car can just follow basically these curves belonging to this space are slower speeds, and this is slower, and on the left is faster. So in this particular case, the green vehicle can just follow the lead car, and let's see what happens. So the cyan car can never cut in front of green car, and green car can still do cruise control again. So this is trained from the output of PredictionNet used as a simulator. And you can see that this changes a little bit because at different times it becomes green. Also, so this shows what happens if we don't reward, if we don't punish cut-ins, and then the cyan car can actually move in front of the green vehicle. And again, these cars are controlled by PredictionNet. We do a little bit of a custom nudge to convince it to change to the lane. And we can test these scenarios in the drive simulation. In this particular case, we use a simplified drive sim with less rendering because we focus on specifically vehicle dynamics and this scenario. Right, and then just coming back to where I was in the beginning, we propose that it's possible probably to use deep neural networks across the whole stack, specifically perception, prediction, and planning. And it may capture complexity of the world in a better way to learn from data. One important note for autonomous vehicles that certain things are not even present in the data, like crashes and rare events. We don't observe certain things in the data. So in this case, we actually have to either use safety checks, extra safety checks between these modules to take care of these rare cases, or introduce these rare cases in our data as a sim to real or as a kind of simulated data. But we think that it's possible to formulate this whole stack as one long deep neural network based pipeline. You can train it in parts and you can fine tune it as a whole, given that most of these operations are differentiable. You can force representations between these layers into human understandable representations so that it's easier to verify and do safety checks. And with that, thank you. I'm done.
Okay.